This video is about biconditional statements and definitions. So a conditional statement is an if-then statement. So for example, if a figure is a triangle, then it has three sides. So all we want to look for with a conditional statement is that it starts with the word if and then has a then part. We call the first part of the statement the hypothesis. And the last part of the statement, the conclusion. And sometimes they'll write it with just letters. They would say if P, then Q. Just because mathematicians are sometimes a little bit lazy. They're like, hey, I didn't want to write an entire sentence, so let's shorten it. So P stands for the hypothesis, Q stands for the conclusion. Then they got even more lazy and just wrote it like this, P, then Q. So there's a couple ways you can write these hypotheses and conclusions. So the converse is if you flip the statement. If you just take the conclusion and put it in the if part and take the hypothesis and put it in the then part. So the converse of this would be if a figure has three sides, we can't just say it. So we're going to have to change it to a figure has three sides. Then it is a triangle. Okay, so now the converse, we've flipped it, which means if we were to write it using just our letter notation, we would say if Q, then P, or you could write it even more simply as Q arrow P to say if Q, then P. So a biconditional is when both your conditional statement and your converse statement are true. If they're both true, you can combine them together into one sentence instead of having to write two separate sentences. So let's decide if they are true. If a figure is a triangle. So it helps me to draw this out. Okay, here's a triangle. Then it has three sides. Well, looking at our shape, we have 1, 2, 3 sides. Okay, our conditional part is true. Converse is if a figure has three sides, then it is a triangle. So let's try drawing something with three sides. Here's one, here's two. Got to connect the two to make it a figure. Well, that's a triangle. So the converse is also true. If it has three sides, then you have to draw a triangle. That means we can now write our biconditional statement. That combines them both together into one sentence only. To do that, we say a figure is a triangle, so we're using the hypothesis first. And then here's the keywords that makes a statement a biconditional statement. A figure is a triangle if and only if it has three sides. So we wrote our hypothesis first. We used the words if and only if to say, hey, this would work either way, whether we wrote it as a conditional or a converse. And then we wrote the conclusion. So again, we could just do this with letters. We could say, oh, sorry, I have to write this a little bit differently. P, if and only if. Q, or you can do the arrow, but this time since it's reversible, since we could go either way, the arrow has to point both ways. So the biconditional would replace the conditional and the converse statement. Instead of needing two sentences to say this, the biconditional puts it down into one sentence. But you can only use the biconditional if the conditional and converse are both true statements. So let's look at this conditional. If a figure is a square, then it has 4 sides. So let's think about that. Okay, our figure is a square. I'm going to draw a square. How many sides does a square have? Well, there are 1, 2, 3, 4 sides, so this statement, true. It checks off. Converse, so then we flip it. We say, if a figure has 4 sides, then it is a square. So let's check it out. So I draw a shape with 4 sides now. This one has 4 equal sides. Yes, it is a square. I have to think, is there any way I could draw a shape with 4 sides, any way at all, and it's not a square? So there's actually a lot of examples we could do that wouldn't work. So this is called a counter example. It's showing, hey, this doesn't work. I have 4 sides here, but this is a rectangle instead of a square. That means this does not check out. The converse is not true, and it means we have no biconditional. It doesn't work because one of them are false. So we kind of have some options. We can write a biconditional if both are true. If only one is true, we can never write a biconditional. If one is false, there is no biconditional. And if both are false, there's no biconditional. So the only time you can write a biconditional is if both are true. And you may have thought of a different counterexample. It can really be anything that has 4 sides but is not a square. Like I could do a parallelogram, there's the kite, there's lots of shapes that we could have used as a counterexample to that statement. So something else they may ask you to do is to test to see if a biconditional is true. So they're going to give you the biconditional first, x squared equals 9 if and only if x equals 3. And we're going to have to split it up and write the conditional statement and the converse and see if each of them are true. So conditional would be if, then. We know conditional starts with if and then moves to then. And we take our hypothesis, which was written first. Remember, that would be P, that's our hypothesis, and Q, that's our conclusion. So if x squared equals 9, then x equals 3. The converse of that, if x equals 3, then x squared equals 9. So we have to decide, are both of these statements true? If there's even one that's not, this biconditional does not work. So if x squared equals 9, then x equals 3. So we may think that's true, because if I plugged in 3 here, 3 squared is 9. But we need to think, are there any other options? So remember with squared, the opposite of squared is to square root. And when you're square rooting a number with an equation, you actually have 2 answers, a plus or a minus 3. This could also be a negative 3 because negative 3 squared means multiply negative 3 times negative 3, which is positive 9. So this statement is false because even though x could be 3, could also be x equals negative 3. Okay. Converse statement. Let's check to see if that was true or false. If x equals 3, then x squared equals 9. So this one, we already know what x equals, and we would just have to plug it in. If I plugged in 3 here, well, 3 squared is 9, so that one is a true statement. So this one does not work because one piece is false. So one more biconditional statement, and then we will move on to definitions. So again, test to see if this biconditional is true. So I included this one just in case you've forgotten what these symbols here mean. Those are absolute value bars. And what they do is they take whatever number is inside and make it positive or keep it positive. So absolute value of positive 2 is still positive 2. Absolute value of negative 2 becomes positive 2. They make every final answer positive, no matter what you started with. So we have to write out our conditional statement and our converse statement and check to see if they're true. Conditional. If we find the hypothesis, the first part, absolute value of x is greater than 0, then x is greater than 0. The converse would be if x is greater than 0, then absolute value of x is greater than 0. So if absolute value of x is greater than 0, well, let's look at the ones we just did. Absolute value of positive 2 was 2, and we ask ourselves, is 2 greater than 0? Yes. Okay, what about the other one? If absolute value of negative 2 is positive 2, we ask ourselves again, is 2 greater than 0? Yes, it is. So just for the hypothesis, I was running out of room, but this was all just thinking about the hypothesis still. I could have used x equals 2, started with a positive 2, or I could have used x equals negative 2 and started with a negative 2. So now we check our conclusion. So I said, well, I could have started with 2. So plugging it in, 2 greater than 0. That's still true, that still checks out. I could have also used negative 2 to start with. So then I say, okay, is negative 2 greater than 0? Well, that's where it falls apart. Negative 2 is not greater than 0, it's smaller than 0. So that's false. So our conditional statement is false. We already know the biconditional doesn't work, but we need to check the converse still because it gives you multiple choice options. And two of the options, one will be this doesn't work because one is false. One will be this doesn't work because both are false. So we just have to check both. So if x is greater than 0, well, that means it has to be bigger than 0. That means I'd have to use the 2 to start with. And actually, I should not say the absolute value yet because we're not going to be looking at the absolute value yet. The negative 2 is not greater than 0, so it doesn't work. So 2 greater than 0, then absolute value of x is greater than 0. So if I take the absolute value of 2, we know it comes out to be 2, which is still greater than 0. So this is true. But we still can't use the biconditional statement. Sorry about that, I accidentally moved where the screen was recording. We still can't use that biconditional because there was one part that was false. So with our definitions, a good definition includes a lot of detail and it would work as a biconditional statement. So here's an example of a definition. Congruent angles are angles with equal measure. So we're going to write this as a conditional statement and write the converse and see if it could be written as a biconditional. If it could be written as a biconditional, this is a good definition. So we have to write our conditional statement first, starting with our hypothesis. If so congruent angles are angles with equal measure, this is the basic start of our hypothesis. I would say maybe if two angles are congruent, you kind of have to change the order around so it makes sense as a sentence. Then they have equal measure. So let's check that. If two angles are congruent. Congruent means they are the same angle. Congruent means they're the same shape, same size, so they're the same angle, which means they would have to have equal angle measure, because that's the definition of congruent. So now we write the converse. So that one checked out. If two angles have equal measure, then they are congruent. So, again, if they have equal measure, that means they're the same shape. If I draw a 30-degree angle, even if I rotate it, I still have to open that angle up the exact same amount for it to still be 30 degrees. So it can be rotated and stuff, but if I were to rotate it back, oh, sorry, it grouped them together, so I can't just rotate it using, but if I were to rotate it back, then it would match exactly. Obviously, I'm drawing them by hand, so they don't necessarily match because I drew them by hand, but if I had actually measured the 30 degrees, it would have to match exactly. So that one checks off as well. If you can write a biconditional, this is a good definition. So the last thing is you can take something and decide, hey, this is going to be a bad definition because I can think of a counterexample. So this is the definition we're given. The letter Y in American Sign Language, that's why we have all the hands there, so people who cannot speak or hear will sometimes use American Sign Language to communicate using their hands. The letter Y is formed by extending the thumb and one finger, and the other fingers are folded into the palm of your hand. Identify the counterexample. So this was the letter Y, just so you could see what it looked like. The thumb is extended, one finger is up, and the fingers are folded into the palm of your hand. So we want to see if this is really a good definition of how you form the letter Y or not by looking at these and seeing if any of them work as a counterexample. So the letter D, I notice right away, hey, this does not have the thumb extended. That means it can't be used as a counterexample because it would have to follow the definition but not actually be the letter Y. So this didn't even follow the definition. I throw it out. Okay, what about the letter L? Okay, by extending the thumb is extended, so that piece checks off. We have thumb extended. And one finger extended. There is one finger extended. The other fingers are folded into the palm of your hand. That also checks off. So this letter follows the definition, but it's supposed to be the definition for the letter Y, and that's the letter L. So this one is our counterexample. It's saying this definition you had for Y doesn't actually work because the letter L could be mistaken for the letter Y according to that definition. The letter S again doesn't even follow the definition, so it's another one we would throw out. It doesn't have the thumb extended or one finger extended. So that ends our discussion on biconditional statements and definitions.